can have lunch. So, nice to meet you. I am Gabriel. I am from UFPR. My supervisor is Professor Thiago de Lima Prado, and I will present a work that's a collaboration with Professor Miguel San Juan and Professor Sergio Roberto Lopes. So, I am from physics, but I work on computational neuroscience. And the idea is that I can use this basic phenomena from sound waves, that is bit frequency, to induce interesting phenomena on a synchronization dynamics, on a intermittent phase synchronization dynamics. So, just to remind you what is bit frequency, I will introduce this phenomena called pendulum waves. So, if you have a sequence of oscillators and they have a phase frequency difference given by a specific gap, like here is delta f, and for the work will be delta f. So the frequency difference between any oscillator will be an integer multiple of delta f, and you can devise it only using this shape that's based on this equation, right? So this is for pendulums. So when you have this this thing, you see this interesting phenomena where the oscillators are out of sync, and for some instance, they phase mesh. So this is not due to coupling, this is just incidental phase mesh, and we try to explore this phenomena to induce phase transition. So this is the question. Can we exploit this incidental phase mesh in a network of oscillators? So now I introduce the network. That is, So if I want to apply this for a model, I need to rewrite this in terms of some parameter. So I'll make some assumptions. So for two sine waves, for example, the bit frequency is just the difference between them. But if you have a lot of frequencies, a lot of oscillators, I need to take into account all the possible bit frequencies between each pair of oscillators. And then if I make some derivations, I found that all the bit frequencies follow a simple formula that is based on this TB here, that's the preferential bit time. And all the other bit times are just divisors of this quantity. So this is the bit time that's the most frequency for the network. And it is written in terms of the number of neurons or number of oscillators, the heterogeneity range you choose for the network. So the oscillators must have different frequencies, so they must have different parameters. And then we make an assumption that the frequency response is linear. So quite simple formula, right? I can show that this time is the most probable for the network. Okay, so the model I used is the Izekevich model. That is the one I was used during my master's. So this was our first attempt. Now we are trying to generalize for other models, but we choose the Izekevich model because it has a good biological plausibility. So it can reproduce a lot of neural firing patterns. While it is simple, it has just two variables, and it's quite simple to implement. So these are some examples of firing patterns the Izekevich model can reproduce, and we focus on this chattering pattern, or we call also bursting pattern, that is periodic when the neuron is uncoupled. So this is network equation. So Izekevich model has two variables. That's V, the membrane potential, that's the quick variable, and U, that's a recovery variable. And when we couple the neurons, we introduce this forcing term here that for our case is just the mean field coupling. So it has a bias, and it has a coupling term that depends on the coupling strength gamma. So when gamma is 0, the neurons are uncoupled, and we expected an unsynchronized network. So we need the bias, so when the network is uncoupled, all the neurons still oscillate. So for the case of this work, we choose this bifurcation to explore, where the neuron before the bifurcation has 4 spikes per burst, and after the bifurcation it has 5 spikes per burst. What it does is that the frequency gets a little lower when it has 5 spikes, because each burst needs to accommodate 1 more spike. So even though you change the parameter just a bit, like here, the frequency will have a huge jump because of this bifurcation. So I show here 2 frequency response curves. So the solid line is for a high bias, and the dashed line is for a low bias. So you see that for a high bias, the bifurcation occurs because it stimulates more spikes, and for a low bias, the bifurcation doesn't occur. So this is important because one of the explanations for the phenomena is that when the network is coupled, each neuron can behave like in one branch or in the other. So during the dynamics, each neuron can display only 4 or 5 spikes per burst. It limits the possible frequencies for each neuron. So here are just some examples for the individual dynamics. So to have something similar to pendulum waves, we need to accommodate the parameters in our network in a specific way that follows a gap. So I will have a minimum parameter and a maximum parameter, and in the middle I will have the bifurcation. And once, it's almost linear, right? So I will have a gap in the parameter that will generate a gap in frequency. So in our network, every neuron will always have an integer multiple of this specific gap. And also, because of the bifurcation, I can classify the neurons into 2 groups. The group 1 are neurons before the bifurcation, and group 2 are neurons after the bifurcation. So from this picture, you see that after the bifurcation, some neurons will have access to some property easier than others because of this gap. So this is just a picture of the network. I have one cluster, another, and mean field coupling. So to measure phase synchronization, I use the Kuramoto order parameter. So to be quick, I just associate a phase to each burst, and I put it on a complex plane. Then I use the mean, and the absolute value of it gives an idea if the oscillators are pointing to the same direction at each instant in time. So this is an amazing measure for phase synchronization. And once the neurons are periodic, it's easy to set a threshold and say exactly when each burst begins and when each burst ends. So it's based on a previous work where we explored the parametric space for this network, and I can show that when I increase the coupling strength and then decrease the coupling strength, I have an hysteresis here. For large networks, here for 1,000 neurons, this hysteresis is well defined, and the network is robust. So if I begin for a synchronized network, it stays there, and it's not easy to apply noise to remove from this state. But if the network is small, it's easy to jump from one branch to the other. So it's sensitive to noise and also to just random fluctuations from the dynamics. And then I want to explore the intermittent case, right? So I will focus on these critical dynamics when power laws are expected to appear. There. So at that critical dynamics, this is the phase, the time evolution for the neurons. So yellow dots here are bursts, and blue dots are quiescent periods. And on the below panel, you have the Kuramoto order parameter time evolution. So you see that there are times that half of the neurons, so are there neurons after the bifurcation, they synchronized. And after some times, these neurons will desynchronize, while there are some neurons that never synchronize, and the explanations for that is that I did something similar to noise to induce transitions. And then the interesting dynamics occurs for the second group that has easy to reach that bifurcation and to change the number of spikes per burst, so it jumps from one side of the bifurcation to the other. That's quickly, it's easier to see here. So there's a lot of information. So first is the Kuramoto order parameter for each group. So red, the group that intermittently changes the states. Black for the entire network, and blue for the first group that doesn't transit, so it's not interesting. So focusing on the second group, you see that in this below panel that when each line corresponds to a neuron, and then you have time. So when the network is desynchronized, you see that the colors are the burst frequencies. So the frequencies are lower for the first neurons, and then they increase. This is just because I put the network frequencies in this way. So it's a linear allocation. Right, okay. So when the network is synchronized, the interesting phenomena happens. So you see that this group is phase synchronized, but they change frequencies. So they are never at the same frequency. So even though they are phase synchronized, they are not frequency synchronized at each instant. But if you make the average of these frequencies, you'll see that, of course, they are on average the frequency match. But you see that at each instant, they do not necessarily frequency match. They only phase match. And also, you see that, for instance, these neurons here, I do not show here, but like here, they have 5 spikes per burst, and these other frequencies associated to 4 spikes per burst. Then, what are the residence times probability distributions? So you can use the discrete gaps, as I showed, and you can compare to a usual random distribution of parameters. So the random distribution of parameters always gives something similar to a Power law, how like it's expected. So everyone shows Power laws when there is intermittent dynamics, right? But when you have a frequency gap between the oscillators, you see that there are peaks on the probability distribution time. So at this instance, the network has a huge probability to transit and to change states, while some subsequent period of time, the probability is quite low. So this is in log scale. So almost all the residence times are in this 1,000 seconds period. So this is quite interesting, and it works not only to transit from the unsynchronized to synchronized, but from partially synchronized to unsynchronized states. And also, we can fit this. So on our model, we can change some parameters, like the number of neurons, and then measure these probabilities. And we see that that first equation for the ensemble of oscillators matches the peaks on the probability distribution times. And when we fit it, we find this frequency response. And the question is, which frequencies or which neurons follows this frequency response? And then we can show that there are the neurons from the second group. So here you see that the dots are the mean frequencies. So they match mean frequencies when they are synchronized. The magenta color are the frequency distributions when synchronized. And the yellow color is the frequency distribution when unsynchronized. And you see when these neurons are synchronized, they have a bimodal frequency distribution where the most probable are far from the mean frequency. Then we show that there are these 2 frequency modes here that follows that frequency response. And then the bit frequency, we can explain that the bit frequency can explain the phase transition in this model from unsynchronized to partially synchronized state, and also from partially synchronized from unsynchronized state. That was not expected, and we do not have a complete explanation for that yet. So this is quite interesting, because even though the oscillators are in phase, they retain the intrinsic frequency difference I imposed at the beginning. So this is a quite interesting state for the network. So the conclusions is that we can explain the peaks on that probability distribution using the bit frequency formalism. And the next step is to explain better these mechanisms where the oscillators can phase synchronize while they have different instantaneous frequencies. And also, we want to apply to this phenomena. That's the Bissing fundamental illusion. That I think there is not a closed solution for that. And we have similar times here. And that's all. I would like to thank my university, Universidade Federal do Paraná, my credit program, CAPES, CNPq, and you all for your attention. Thank you.
Thank you, Gabriel. Do we have any questions? Please. No? Oh, okay.
All right, so can you go back to the slide of the probability distribution with the parallel decay? Because at least for me, in the first panel, it looks like more an exponential decayment than a parallel decayment.
Oh, yeah, probably it is.
All right.
But yeah, we are focusing on the peaks, so.
All right. So just like.
Yeah, I don't know what it would mean if it's exponential or parallel, but.
Yeah, it's a random transition probably. It occurs anytime. So I think it's just this observation. But
yeah,
thank you very much for the work.
Thank you.
I have a trivial question, probably.
Okay.
Why do you use Izikevich, which although is a linear system, the nonlinearity comes in the discontinuity, and do not use something like the Chialvo model, which is so simple. It has a nonlinearity, but of course it has to have. But it's, I mean, what is the advantage of the Izikevich over the Chialvo, for instance?
The advantage is that first I observed this because I was studying the Izikevich because of the lot of patterns that it can generate. Actually, it's quite similar to the integrated amplifier, right? So, oh, sorry. Okay, so first I observed this, and it was hard for me to find similar bifurcation like this here. So I looked for several models. I found something similar in the Hindi-Marsh model. Yeah, that's a problem. So, yeah. When I go to simpler models, I have less parameters to explore, and then it's even harder to find this kind of bifurcation. Because it's a specific bifurcation. I have a bursting dynamics, where the bursting are periodics, and they gain a spike and remain periodic for a wide range of parameters. So I don't know if the Chialvo would behave like that. Yeah. Thank you.
On slide 16, I couldn't grasp what's the difference between, what were you varying amongst them to find the...
Each panel is a network size. On the x-axis is the coupling strength. Y-axis is the Kuramoto order parameter.
Okay, thank you. Thank you.
Okay, I have a question. In the last slides, you were talking about time. Is that computational time? What time is that? Time, yeah, that time, in seconds.
Oh, it's in seconds because the Izikevich model is divided so V variable and time has dimension. So when time on the Izikevich model, time is milliseconds, the V is millivolts.
Okay.
Yeah, millivolts, yeah.
Good, thank you. Any questions? No? Okay, let's thank Gabriel again.
Thank you very much.